Hi guys, my name's Apurva and I'm one of the managing directors at Helix. And I just like to preface this before I get started by saying that thank you guys for keeping up with the lessons. The curriculum team put a lot of hard work into this, and without further ado, we're going to start our infectious disease epidemiology, measles, and vaccinations lesson. And I guess just to start out, is um, what exactly is infectious disease epidemiology? So epidemiology is actually the study and analysis of the distribution patterns and determinants of health and disease conditions in defined populations. It's often used to shape policy decisions and help identify risk factors for disease to improve and develop preventative health care and intervention. And also the epidemiology of infectious diseases is studying the distribution patterns and determinants of those diseases and agents. In addition, we kind of want to define infectious diseases for you. You see here on the slide. Infectious disease is defined as an illness that is due to specific infectious agents or its toxic products that arise through the transmission of that agent or its products from an infected person, animal, or reservoir to a susceptible host, either directly or indirectly through an intermediate plant or animal host, in other words, vector, or the inanimate environment. And we'll talk a little bit more about that. And infection is definitely a term that you guys have probably heard, especially regarding the COVID-19 infection. But it's formally defined as the entry and development or multiplication of an infectious agent in the body of humans or animals. Infection is not synonymous with infectious disease. The result may be inapparent or manifest in different ways. So moving on, this is a really interesting topic that epidemiologists usually discuss, and that's the epidemiology triad. And just to dive right in, when we study epi and the distribution of diseases, we typically use this, which focuses on these kind of four elements, which are the host, the agent, and the environment, and how it's kind of connected with the vector, which is the mode of transmission. But in recent years, it's been deemed too static because it fails to capture the dynamic nature of infectious diseases. And in an infectious disease paradigm, we would rather focus on the interaction of these nodes in the host, agent, and environment in a more dynamic way to think about and study infectious disease epidemiology. So the chain model is definitely a better way to study infectious diseases nowadays. And this is the chain model, which kind of looks at key components that have been linked to new infections occurring. And this starts out with the susceptible host, which you guys can kind of, I don't know if you guys can see my mouse, but right here I'm circling it. And this is referred to as host defense mechanisms that could be innate or acquired immunity through vaccinations. It really depends on how susceptible the host is. And I think you guys can think of various ways that this can change based on age, gender, etc. And the next step in this chain model is the causative agents, which could be microbial agents, prions, or toxins. And the next kind of chain is the reservoir of source, which agents normally live or multiply, and they could be either living things or they could be inanimate, like soil or water. And the source of the location of the path, this is actually the source of the location of the pathogen prior to transmission. Um, and the portal of exit is kind of next in our chain, which could be anything from the GI tract to the respiratory tract, the urinary tract, and it could take the form of lesions, blood, your genital secretions. There's a variety of ways that the disease can exit the body and be ready to enter another person's body. And the mode of transmission there is kind of the key, where it's the transmission point from the host to a new susceptible host. And the portal of entry here could be either the same portal of entry that the portal of exit is, or it could be a completely new one. But all in all, this chain model kind of describes the integrated series of events that has to happen for new infections to occur. So a quick example of this maybe is the flu. And as you guys know, the flu is especially deadly to the elderly. Let's just run through a scenario where we can kind of classify each chain here in the flu transmission. So the causative agent is definitely influenza. The reservoir source could be a variety of animals and humans. So it could be humans, birds, swine. I think you guys have heard of these different types of flus before. You know, they were super prevalent back in this century for being some of the most watched diseases before COVID-19 pandemic came around. These kind of represent the past pandemics that have occurred throughout our lives, at least. So the portal of exit in this case, as you guys might know, is the respiratory secretions or just respiratory droplets that are very similar to COVID-19, how COVID-19 is spread. And the modes of transmission, again, like I mentioned, are droplets or airborne. And the portal of exit, again, is the respiratory tract. You would breathe in these droplets or tiny airborne particles as well that are a little bit smaller than the droplet size. And you guys can then it can reach the respiratory tract, which then can cause infection. And the susceptible host can include the unvaccinated, and again, like I mentioned, the elderly and also children. So moving on to kind of a little bit more, sorry, I should have shown you guys this, but this is the chain model for influenza. So moving on, this is kind of the little tidbits of how epidemiologists measure disease. And this was especially interesting when COVID-19 first started. This R naught was a super prevalent, and yeah, it's said R naught, the R zeros R naught. But it's the basic reproductive number of a disease. How many new people does a single host infect successfully? So that's really what the R naught is telling you. So a little bit more formally though, it's definitely an important characteristic to consider in how fast a viral outbreak or pathogen outbreak, to be more broad, can be extinguished. And it's kind of defined as as the number of people that one sick person can infect on average. And you can see kind of some of the maximum R naught values for different diseases. Measles being, of course, one of the most contagious diseases known to mankind, with an R naught value of 18, meaning one host on average would infect 18 new folks. So to be a little bit more definition-y, the R naught is an expected number of new infectious hosts that one infectious host will produce during their infectious period in a large population that is completely susceptible, meaning that this doesn't really include new cases produced by secondary cases. And moving on to kind of the point of this lecture, which is the measles and vaccination, how we kind of took vaccines and put it in the hands of the majority of the population, that now we can actually combat disease by affecting that R naught value that we talked about, rather than more downstream solutions such as treatments. This is really a preventative approach. So what exactly is measles? To preface, I think it's a really old disease that really isn't prevalent anymore because of the massive vaccination campaign that we'll talk about pretty soon. But measles is one of the scariest diseases, probably. It's an infectious viral disease that lives in the mucus of your nose and throat, and you can be contagious for a week before and after being contaminated. And it's spread in droplets on the air or also on surfaces, much like COVID-19. And it's definitely highly preventable, sorry, with vaccines, and it's usually administered in a 2-dose sequence similar to COVID. So I think the funny thing about measles is it's especially prevalent in children, but it's really rare in the US because of the massive vaccination campaign. And yeah, it's dropped over 99%. Some of the symptoms of measles are very flu-like, It includes a high fever, runny nose, cough, congestion, red eyes, and the telltale sign here is the skin rash that covers the entire body. And some of the complications that occur more downstream at later stages of the disease are middle ear infection, croup, which is it's an airway infection that affects breathing, pneumonia, diarrhea, lung infections, death, all cheery things. However, this isn't really everything's on a continuum. Their vaccination, as you know, is not always universally agreed upon. And there have been several measles outbreaks over the recent history. So this graph kind of shows the number of measles cases per year. It's kind of weird, these little blips and kind of some of the states that have been recording cases in the past are California, Colorado, Connecticut, Georgia, Illinois, New Jersey, New York, Oregon, Texas, and Washington. And 2014, as you can see here, is kind of one of the interesting years, but there's definitely there was 23 measles outbreaks in 2014, and one especially large one were in communities of unvaccinated Amish communities in Ohio, where 383 cases occurred. And many of the cases in 2014 were associated with cases brought in from the Philippines, which had a particularly large outbreak that year. In addition to those Amish communities that faced a particularly deadly wave of measles, folks in California, in Disneyland specifically, you might hear about this in some of the future classes you guys take. That was also kind of driven by a large unvaccinated children population in Disneyland that allowed for that spread to occur in close confines, such as rides and amusements, and also some in Utah and Ohio. So from the Californian cases, which were about 119 cases, 45% of those folks that actually became ill were unvaccinated, and the first person to be reported in that outbreak was an 11-year-old unvaccinated child. This isn't really contained to the US. The US is obviously a very wealthy country that can afford to vaccinate its population, but there are several international outbreaks that have also occurred throughout the years. So France in 2018, another very developed country, rather rich and often from the fruits of other countries' labor, of course, similar to the US. That is not to say that a lot of folks in France are similar in ideology to Americans in the divide, that some folks don't get vaccinated, some folks do get vaccinated. And in 2018 in France, more than 2,500 cases of measles occurred. And in most of those cases were children who weren't old enough to get vaccinated, strangely enough. In 2019 in Kazakhstan, there was a travel alert for people from the US to get vaccinated before leaving. And previously, 2,300 measles cases were registered in Kazakhstan during the 2015 to 2016 year. Another interesting recent development is Ukraine 2018, where a little under 50,000 people were diagnosed with the measles virus. The most recent really severe outbreak, though, was in Madagascar from 2018 to 2019, where about 50,000 people were infected and 300 were killed by the measles virus. Most of them were children. And yeah, let me just play this video really quickly, just so you guys can get kind of a insight into the different variables that affected people's I don't think it's loading right now, but if you guys are interested, I'll include the link at a later time, and you guys can spend some time looking at that video. Sorry, my signal is a little bit bad here, but to move on, Vaccines against measles were super effective, as you can see from kind of the reduction in cases in America, at least. So the vaccine against measles is known as the MMR and the MMRV vaccines. The MMR vaccine protects children and adults from measles, mumps, and rubella, and the MMRV also additionally protects against chickenpox. So the 2 doses of MMR are 97% effective at preventing measles, and 1 dose is about 93% effective. And it does induce lifetime immunity. So outbreaks often happen in areas that aren't vaccinated enough. So recently, this includes places in Europe, Africa, and South America. And you might be wondering, why this is true. And the real secret is what we talked about earlier with the R naught values, is it's an extremely contagious disease. If one person has it, then 9 out of 10 people who are close to that person who aren't immune will also get measles. So this is an extremely seriously fast spreading disease that doesn't really take any anything for granted when you are infected. And to go a little bit more deeply into what actually vaccines are. Vaccines are preventative measures that people can take in order to avoid a disease in the first place. And it's a preparation that activates and stimulates body's immune system against invading infectious agents. And they're really what has allowed infant mortality, childhood mortality to significantly decrease over the years. And I think that there are, from this graph here, the vaccines are really improving in their efficacy. And the history of vaccines, however, isn't really as clear cut. I think that it's quite interesting to see how the history of vaccines have developed. So, over the years, there's been several vaccines that have actually induced seizures and death in some cases. So this includes the pertussis vaccine, which was especially a source of vaccine hesitancy. And it's kind of led to lower uses of vaccines, historically speaking. And nowadays, the DTP vaccine is being implemented. So there are several types of vaccines. Most vaccines that we kind of associate with vaccines are prophylactic vaccines, which stop infections from occurring in the first place. So one example is the influenza vaccine, which you guys may have received in the past or may be receiving every year. And they cause antibodies to develop in the body about 2 weeks after vaccination, and these antibodies provide the protection against the infection in the first place. And then the other type of vaccines are therapeutic vaccines. So they're given to individuals who have already been infected, and it stops the disease from progressing to further stages. So one example that was particularly groundbreaking was the HIV/AIDS vaccine, and another one is rabies, which you may know someone who has gotten a rabies vaccine in the past. Another kind of distinction is in the vaccine types or inactivated vaccines. This kind of this in inactivated vaccines and some of the diseases that this is used for are listed. Inactivated vaccines usually a killed virus of the germ that causes the disease, and they usually don't provide immunity that's as strong as live vaccines. So you might need like several vaccines over time, kind of like, as you know, the flu you need to get every year. Another type of vaccine is called a live attenuated vaccine. So these are some of the, MMR, rotavirus, smallpox, and they use weakened forms of the germ that causes the disease. And these are so similar to the natural infection that they help prevent, that they could create really strong and long-lasting immunity. Just 1 or 2 doses over a lifetime can 1 or 2 doses of this kind of vaccine can produce a lifetime of protection. The other kind of new development is and I think you guys have heard a lot about it in the recent past, is mRNA vaccines, specifically used against COVID-19. And these mRNA vaccines make proteins after implementation in the body to trigger an immune response. So they have several benefits compared to other types of vaccines, including the shorter manufacturing times because they do not contain the live virus, and no risk of causing the disease in the person being vaccinated as well. Another type of vaccine, which is the last one, is the subunit recombinant polysaccharide and conjugate vaccines are kind of all grouped together in one umbrella. And they use specific pieces of the pathogen. That's like the protein, some of the sugar elements, or the capsid, the actual casing around some of the viruses. And because these vaccines are only specific pieces of the pathogen, they can give a very strong immune response that's targeted to these parts of the vaccine, the pathogen. And they can be used on almost everyone who needs them, including people with weakened immune systems and underlying conditions. Some of the other ones that are listed here include the toxoid vaccines. So these use the toxin byproducts of some of the pathogens, and they create immunity to parts of the germ or pathogen that causes the disease instead of the actual pathogen itself. The last one is the viral vector vaccine, which again has been used for COVID-19, and these use modified versions of different viruses as a vector to deliver protection. So several different viruses are used continuously for vectors, including influenza, vesicular stomatitis virus, so VSV, measles, adenovirus was used for COVID-19, which causes the common cold. So I think we're going to move a little bit into how viruses or vaccines, my bad, have been prepared. So the primary way that we do this is cell cultures. So primary cell cultures are obtained directly from tissue slices, and they have a really limited cell lifespan. So this is anywhere from 5 to 20 cell divisions. And the FDA regulated that for viral vaccines, you can only use PCC, such as monkey kidney cells, cell lines, and fertilized chicken eggs. You can't actually use cancer cell lines, irradiated cells, carcinogenic chemical treated cells, or mutagenic cells. And this kind of limits the type of cells that the vaccine producers can use. But to kind of go over what the ideal vaccine would look like, it would be definitely safe with minimal side effects. It would provide a lasting protection against specific pathogen. It would activate the immune system and cells in general, and or induce specific antibodies. It would be cheap, stable, and economically available, and it also should be easy to administer. It's kind of difficult to provide worldwide availability for vaccines, especially in less developed countries, the New South, that suffer from diseases because they cannot get access to this healthcare necessity. Vaccines cost both time and infrastructure and money, of course. So manufacturers need those partnerships and communication with countries. And one statistic that's particularly alarming is that 2.5 million deaths a year continue to be caused by vaccine preventable diseases, mainly in Africa and Asia, and children less than 5 years old. And so if you guys have any questions at all, feel free to email me at apurvaprasad7@berkeley.edu, or you can shoot them to your discussion leaders as well. So definitely be thinking about this. Definitely be thinking about this in the future. It'll definitely come in handy, especially when you can show up your friend knowing more about COVID-19 vaccines, for example. I don't know how helpful that would be in colloquial terms, but thank you for listening, guys, and have a good day.